Hello everyone, let's analyze. So today we're going to talk about the change of variables theorem. Of course, in order to talk about the change of variables theorem, we should discuss what a change of variables is. And in fact, it's a function that we've seen before. It's a function that is one-to-one, is class C1, and whose derivative is invertible for all x in the domain U, which is to say that the determinant of the derivative is non-zero for all x in U. Right, so this is exactly the type of function that is invertible. In other words, g has an inverse. So we can think of a change of variables as a continuously differentiable and reversible deformation of some open set U. So let's give the change of variables theorem. Suppose that A in Rn is open, bounded, and has volume, and that g is a change of variables with the property that the determinant of the derivative and the determinant of the inverse of the derivative at each x is bounded on A. Then if B is the deformation of A by my change of variables g, has volume, and f maps B to R is bounded and integrable, then the composition of f and g times the absolute value of the determinant of the derivative of my change of variables is integrable on A, and the integral of f over B, which remembers the deformation of A, is equal to the integral over A of f composed with my change of variables times the determinant of the derivative and absolute value. Now, by the way, the derivative at each x is a matrix, and that matrix is often called the Jacobian. Right? So we say the derivative at x is a matrix, and it's sometimes called the Jacobian. We also sometimes call the determinant of the derivative matrix at some x the Jacobian. So to avoid any confusion, we'll just keep the derivative notation. Of course, the classic example is the polar change of variables. And by the way, in this formula, right, typically A is a rectangle. Right? Typically a change of variables theorem is employed because we have to integrate over some shape that's not a rectangle, and we want to use Fubini's theorem and integrate over a rectangle. So our hope is that whatever shape we're integrating over can be viewed as a differentiable and reversible deformation of a rectangle. That's typically the approach one takes. So the polar change of variables is exactly such an example. So suppose A is the rectangle of 0 to r by 0 to 2 pi, then the circle of radius r can be formed by the change of variables g, which is equal to r times cosine theta in the first coordinate and r times sine theta in the second coordinate, where r and theta are inside of my rectangle. Thus, the integral of f over the ball centered at 0 and with radius r is equal to the integral over A, and remember A is a rectangle, of f of g of r comma theta, because that's the composition of f and g. It's f of g of my new coordinates. That's why it's called a change of coordinates or a change of variables. I have new variables. Times the determinant of the derivative of g times my d of my new variable, which is r theta. Now, since A is a rectangle, the integral over A can be viewed as a double integral, so long as f is continuous, of f of r cosine theta and r sine theta times r dr d theta. And the reason, of course, we get r, this is likely something you've seen before, is because the determinant or the derivative of g is given by this cosine theta negative r sine theta r cosine theta matrix, and the determinant of this matrix is r times cosine squared plus r times sine squared, which is r, which is why this term became r. And this term is just dr d theta because I'm integrating over a rectangle. So again, this is just to give you the key. And again, this is just to give you the kind of canonical example of a change of variables. So for example, we could use this to compute the area of a circle, right? The area of a circle, or the two-dimensional volume, is the integral from 0 to 2 pi and from 0 to r of r dr d theta, right? I was able to transform my integral over a circle to an integral over a rectangle. That's the integral from 0 to 2 pi of r squared over 2, which is 2 pi times r squared over 2, which is pi r squared, right? So, of course, I'm guessing you probably knew that already, but the goal of today's lecture is to understand why all of the math we just did works, why we can go from a circle to a rectangle by just scaling my infinitesimal d variable by this determinant. So our strategy for proving this is by breaking it down into essentially 5 different supporting lemmas, and then using those 5 lemmas to get to our goal. So lemma 1 says let L be a n by n matrix. Of course, we could also think of L as a linear map from Rn to Rn. Suppose A, which is a subset in Rn, has a volume. Then if I take each vector in A and multiply by my matrix L, right, and call that L of A has volume, and its volume is equal to the volume of A times the determinant of L. Lemma 2. Suppose the change of variables theorem is true for a constant f. Then it's true for any integrable f. Lemma 3. The change of variables theorem is true if the change of variables formula g is linear. Lemma 4. If the change of variables theorem is true for g and it's true for h, and g of a is contained in the domain of h, then the theorem is true for h composed with g. And if h is a change of variables on an open and bounded subset of Rn, that should be subset, not an element of, and C is a subset with volume and whose closure is in U, then h of C has volume. Now, by the way, as I was going through these lemmas, you probably noticed that lemma 3 can be proved straight away as a result of lemma 1 and lemma 2. And if you're watching this with someone else, now would be the time where you can look to your partner and say, oh yeah, I thought that. I thought exactly that. So let's just prove lemma 3 quickly using lemmas 1 and 2. We'll suppose that lemma 1 and 2 is true. Then if g is linear, g of x equals L times x for some matrix L. And the derivative of g is the matrix L. Well, lemma 2 implies we only need to show the result for f equals 1. Well, if f is equal to 1, the integral in the change of variables theorem of 1 over L of a is just the volume of L of a. And lemma 1 tells me that that's equal to the determinant of L times the volume of A. And of course, the volume of A is just the integral over A of 1 times this constant, right? The determinant of L, which was already there. Well, 1 composed with G is just 1, because whatever G of x is, it's going to get mapped to 1 when I compose it with 1. And remember, L is the derivative of g if g is linear. So we've proven the change of variables theorem for this specific case, right? That if g is linear, the change of variables theorem is true. Now, of course, we only proved it for a constant f, but if lemma 2 is true, then proving it for a constant f is enough. Okay, let's go to lemma 1. So we're going to go through and prove each of the lemmas. We already got lemma 3 out of the way. Let's start with lemma 1, where L is a n by n matrix, right? We can think of it as a linear map. And suppose that A has volume. Then my goal is to show that the volume of L of A is equal to the absolute value of the determinant of L times the volume of A. Well, let's begin with the rectangle A and two types of matrices. So L1 is going to look like the identity, except one of the diagonal entries got swapped from 1 to C. And L2 is the identity with the addition of a 1 on some non-diagonal entry. So in fact, if I think of L1 specifically in the context of a linear map, that is, I'm going to think of L1 as to what it does when it's multiplied by a vector x. What L1x is a scaling by C of the jth coordinate of x. L2 times x, again if I think of L2 as specifically a linear mapping, then L2 times x essentially replaces the jth entry with the sum of the jth and kth entry of x. So L2 times x leaves x alone except in the jth entry I'm going to get the sum of the jth and kth entry, where j comma k is the entry where that extra 1 has been placed. So this right here would be the jk entry. Now, if we consider what L1 would do to a rectangle A, well, if A is just the cross product of a bunch of subintervals in each coordinate direction, then each of those intervals remain the same except for the jth one. The jth one gets scaled by C. So all I'm doing is I'm taking my rectangle and taking the jth coordinate and extending it by C. And all the other dimensions of my rectangle stay the same. Therefore, the volume of my extended rectangle is just the absolute value of C times the previous volume of my rectangle. And the absolute value of C equals the absolute value of the determinant of L1, matrices of this type. Now I claim that the volume of L2 of A is equal to the volume of A, which would equal the absolute value of the determinant of L2, because the determinant of L2, because it's either upper triangular or lower triangular, the determinant of such a matrix is the product of the diagonal entries, so I would just get 1. Now, in order to see that this result is true, let's take a look at a picture. So here we have a rectangle, a three-dimensional rectangle outlined in black. And we also see the shadows of this rectangle on the xy plane, the yz plane, and the xz plane. And then I'm going to multiply each entry of this rectangle by the L seen above, which is the identity matrix with the addition of a 1 in the 1, 2 entry. So if I multiply that rectangle by L, well, because this is essentially the identity except for this upper 2 by 2 block, it is only the xy plane coordinates, right, or the coordinates in the xy that are going to be perturbed. Well, and what happens is that specifically in the first coordinate, right, in x1, I'm going to get shifted by the sum of x1 plus x2. But the shift is going to be the same. So the base of this parallelogram is equal to the length of the base of this rectangle. And if I notice that my height, right, the height of my parallelogram is the same as the height of my rectangle. Therefore, the area of this parallelogram equals the area of the rectangle. So, if I look at the parallelepiped that's created by multiplying all entries in my black line rectangle by L, I get the base of both prisms have the same area. And because my z coordinates remain unscathed by L, my height of my prism is the same. So the volume is base times height, and they both have the same base area. Therefore, the volume of this red parallelepiped is equal to the volume of this black rectangle. And that is why we can say that if I multiply a rectangle by a matrix of type L2, I essentially get a tilting in one of the coordinate directions. But if I look at the base in that plane, the area remains the same, and all other coordinate entries remain the same. Therefore, the volume is the same. Now, L1 and L2 are known as elementary matrices. But what if A is not a rectangle? Well, since it's bounded, it can be contained in a bounding rectangle S. And since A has volume, the characteristic function of A is integrable. And because it's integrable, there is an upper sum and a lower sum arbitrarily close to that integral, which is the volume of A. So I can bound the difference of the upper sum minus the volume. Of course, that's necessarily positive, or non-negative rather, to be bounded above by any arbitrary positive epsilon divided by 2 times the determinant of LE, where LE is some elementary matrix. And I can also bound in the same way the difference of the volume of A and the lower sum. And of course, this is necessarily non-negative as well. So let's let V epsilon be the set of all partitioned subrectangles completely inside A. Right? So remember, I have a partition P satisfying this bound. Right? So P is a set of subrectangles. And of those subrectangles, we're going to call V epsilon all subrectangles completely inside of A. And of course, if that subrectangle is completely inside of A, well then the characteristic function chi of A is 1 on the entire subrectangle. So if my function is constant in the rectangle, the infimum over that subrectangle must be that constant, 1. Therefore, the volume of L applied to this rectangle. So because V epsilon is a collection of rectangles, I could take the volume of my linear mapping of these rectangles. Because it's a set of rectangles, I'm going to get just the determinant of my elementary matrix times the volume of all my subrectangles using the result from the previous page. And of course, the volume of V epsilon is precisely the lower sum, because the lower sum of chi of A is the sum of the infimum of A on all my subrectangles, but that's going to be 1 or 0, and it's only going to be 1 if the subrectangle is completely contained inside A. So that's why the volume of V epsilon is my lower sum. Now let W epsilon be the set of all partition subrectangles that intersect with A. Another way of thinking about it is that the union of all subrectangles in W epsilon completely contains and envelops A. So if R is one of these subrectangles, the supremum of the characteristic function is 1. Because each subrectangle intersects with A, the characteristic function chi A must be 1 at some point. So the supremum over the subrectangle is 1. It follows that the volume of my matrix, my elementary matrix L of W epsilon, by the way, this should be L subscript E and should that. So the volume of my elementary matrix applied to W epsilon from our previous result, because now we're just dealing with rectangles, is equal to the determinant of my elementary matrix times the volume of all of my subrectangles added up, which is precisely the upper sum. So if I take the difference of this minus this, I get this minus this. I can factor out my determinant, and therefore I get this difference. And using this result here, I get that that's equal to, well, the determinant of my elementary matrix divided by the determinant of my elementary matrix times 2 epsilon divided by 2, so of course that leaves me with just epsilon. Now since epsilon was arbitrary, this implies that L of A in fact has volume, and the volume of L of A is equal to the determinant of my elementary matrix times the volume of A. So again, to summarize the idea, we proved the result when A was a rectangle. And then if A wasn't a rectangle, we said, well, we can approximate A arbitrarily well with a union of rectangles. And then we can apply our result to that union of rectangles. That's the main idea. Now, of course, what if L is not an elementary matrix? Well, all matrices can be expressed as a product of elementary matrices. You may have seen this result in your linear algebra. It may have been presented using in another context. Specifically, this is often proven when you're looking at LU factorization, which is essentially Gaussian elimination by another name. So if L is a matrix, then L is equal to a product of elementary matrices. Furthermore, the determinant of L is equal to the product of the determinant of my elementary matrices. It follows that the volume of L of A is equal to the volume of L1 of, L2 of, and so forth. And if we just go one by one, I get this is equal to the determinant of L1 times the volume of L2 of times L3 of, and so forth. So I get the product of all of my determinants of my elementary matrices times the volume of A, which is precisely the determinant of L in absolute value times the volume of A. And Lemma 1 has succumbed. Lemma 2. Suppose the change of variables theorem is true for a constant f, then it is true for any integrable f. Proof. Let f be any integrable function on G of A, which is a subset of Rn. Let S be a bounding rectangle of G of A and P a partition of S. Then the lower sum, well, by definition, is the sum of all the infimums of F over each subrectangle times the volume of those subrectangles. Now, the volume of those subrectangles, well, that's just the integral over R of 1. And mR of F, that's just a constant, right? For all x and R, the infimum is, well, the infimum, so it remains constant. Now here's where we use the fact that we're assuming the change of variables theorem is true for a constant f, and mR of f is constant. So if we just apply the change of variables theorem, we get the sum of the integral of G inverse of each of these subrectangles times the infimum of f over the subrectangle times G times the determinant of the derivative of G. Now, because mR of f is the supremum, because little mR of f is the infimum, then the infimum is necessarily a lower bound. So I get it's less than or equal to f composed with G times that determinant of dg over the same integral. And well, if I'm summing integral over subrectangles, that's just the integral over the entire bounding rectangle S, warped by G inverse. And G inverse of S is, well, G inverse of S is not A, but F, right, outside of A, we're assuming is 0. Of course, we're considering an extension to the bounding rectangle. So G inverse of S, when applied to the extension of F, can just be reduced to A, since outside of A I get 0. Now notice this inequality is true for any partition of S. Well, if I take the infimum over all partitions, I still get that this inequality is true. And the infimum over all partitions is equal to the integral of f over g of a, which of course we're assuming to exist, because we're assuming f is integrable over g of a. That's part of the hypothesis of the change of variables theorem. So then the integral of f over g of a is less than or equal to the integral over a of f composed of g times the determinant of the derivative of g. Now, a similar analysis applied to the upper sum as we did to the lower sum would reveal the opposite inequality. So because the integral of f is less than or equal to and greater than or equal to the integral of f composed of g times the determinant of the derivative of g over a, we get equality. So if the change of variables theorem is true for a constant f, then it's true for any integrable f. So if the change of variables theorem is true for a change of variables g and a change of variables h, such that g of a is contained in the domain of h, then the theorem holds true for the composition of h and g. So to prove it, we'll begin with the integral of f over the change of variables h composed of g. Now, of course, that's just h of g of a. Now, by using the fact that the change of variables theorem holds for h, that's the integral of g of a of f composed with h times the determinant of dh. Now, using the fact that the change of variables theorem is true for g, we get this equals the integral over a of f composed with h composed with g times the absolute value of the determinant of the derivative of h composed with g times the determinant of the derivative of g. Well, f composed with h composed with g is just f composed with the composition of h and g. And that, according to the chain rule, is just the determinant of the derivative of h composed with g. So that's just a result of the chain rule. And we have our proof of lemma 4. So now let's take a look at lemma 5. If h is a change of variables on an open and bounded subset of Rn, U, and C is a subset of Rn, has volume, and its closure is contained in U, then h of C has volume. Now, it follows from the fact that h is continuous on U, which contains the closure of C, that h of C is bounded. Thus, it only remains to show that the boundary of h of C is a Lebesgue measure 0. If that's true, then h of C has volume. Thus, we need to show that since the boundary of C has measure 0, owing to the fact that C has volume, then the boundary of h of C has volume 0. So this is our goal. Now, since h is a change of variables, it's one-to-one and locally invertible. And of course, so is its inverse. So let x be on the boundary of h of C. Then there exists a y in the closure of C such that x equals h of y. Now let V be any open neighborhood of y. Now, maybe V is contained in the interior of C, maybe V is contained in the exterior of C, or maybe V straddles the boundary of C. Of course, we're going to show that it can only straddle the boundary of C. So V is any open neighborhood of y, but of course contained in U because that's our universe for now. Now, because V is an open neighborhood of y, and h of y is equal to x, then h of V must contain x, which is on the border of h of C. Now suppose V is completely contained inside C. Then h of V is completely contained inside the interior of h of C. Right? That's because V is open, and well, if every element of V is in C, then every element of h of V must be in h of C, by definition of what h of C is. And it has to be in the interior because if V is open, then h of V is open as well. But x is not in the interior of h of C. And x is in h of V. So that can't happen. We can't have V be contained inside of C because that would mean that x is not on the boundary. But of course, we're assuming that x is on the boundary. So since y is in V and y is in the closure of C, remember V is an open neighborhood of y, and that open neighborhood cannot be contained completely inside of C, it must be that V straddles the boundary of C. Right, of course, V can't be contained outside of C because, well, y is in the closure of C. Since V straddles the boundary of C, it intersects with the exterior and interior of C. And since V was an arbitrary open neighborhood of y, then y is on the boundary of C, by definition of what a boundary is. Right? a boundary point of a set C must satisfy the property that every open neighborhood around it has a piece of the interior and a piece of the exterior. So if X is in the boundary of H of C, well, that implies that X is in the boundary of H of the boundary of C. Because remember, X equals H of Y, and we just proved that Y is on the boundary of C. Well, that means the boundary of H of C is contained in H of the boundary of C. Applying a similar argument to H inverse, which has all the properties of H, would show that the boundary, or rather H of the boundary of C, is contained in the boundary of H of C. Therefore, they must be equal. Thus, boundaries get mapped to boundaries by a change of variables. But does the fact that the boundary of C has measure 0 mean that this property is maintained after getting deformed by my change of variables? Another way of putting this, if H of C has volume, can we bound it by the volume of C and the deformation properties of H? Well, let E be the open ball centered at x naught with radius rho using the infinity norm as our metric. So it's all x in Rn for which x minus x naught is strictly less than rho using the infinity norm or the infinity metric. Recall that the infinity norm of a vector is just the largest absolute value entry. That means E is a cube with edges of length 2 rho and volume 2 rho to the nth power if E is a cube in n dimensions. So the mean value theorem implies that there exists a set of points C1 through Cn on the line connecting x and x naught such that the difference of hi of x minus hi of x naught is equal to the gradient of hi at ci transpose times x minus x naught. So again, this is just a straight application of the mean value theorem on our setting. And this is true for each I from 1 to n. Well then, if I take the max on the left and right of the absolute value, on the left I'll get the infinity norm, and on the right, well, I can bound it by the max over all I, and the max over any possible evaluation of the gradient. Now, because the derivative of h has as its rows the gradient of hi transpose, then this term is less than or equal to the infinity norm of the derivative matrix evaluated at C times the infinity norm of the vector being multiplied. And again, I'm maximizing here over C in E. In other words, let me find the point where the derivative is largest in magnitude. By the way, the infinity norm of a matrix, this is just the induced operator norm. In other words, it's the max value of D times a unit vector in the infinity norm. And because X is inside of the infinity ball of radius rho, this difference is necessarily less than rho, because I'm assuming that X is inside of E. It follows that h of E is contained inside a cube whose edge lengths are bounded by specifically this. That is, they're bounded by a scaling of the edges of E, right? Because E has edges that are equal to 2 times rho. Thus, if h of e has volume, well then its volume is less than or equal to this times 2 raised to the nth power, which would give me this term, and then of course 2 rho to the nth power is the volume of my cube E. Right, that comes from this line here. So now let's return to the measure of the boundary of h of c, which you know is equal to the change of variables formula h applied to the boundary of c. Now, since the boundary of c has a Lebesgue measure 0, since we've assumed that c has volume, we can cover it by a countable union of rectangles whose cumulative volume is less than epsilon. Let m be the maximum value of my derivative matrix in the infinity norm over all x in all of those rectangles. Then those same rectangles, when deformed by h, are themselves contained in a set of rectangles that have a cumulative volume of m to the nth power times epsilon, using the previous page. Thus, the boundary of h of c can be covered by a countable union of rectangles with arbitrarily small total volume, because again, epsilon here is arbitrary and m to the nth power is fixed. Therefore, the boundary of h of c has Lebesgue measure 0. Of course, that means that h of c has volume, which was our goal. And now we've come to the main event. Now, Lemma 2 has bought us some breathing room. Lemma 2 implies that we only have to prove the change of variables theorem for f is equal to 1. In other words, we only need to prove that the integral over a of 1 times the determinant of the derivative of my change of variables is equal to 1 over my change of variables of a, which is of course equal to the volume of my warping of a. Now, note that if L is an invertible matrix and R has volume, then lemmas 1 and 5 imply that the volume of L inverse times G of R equals the absolute value of the determinant of L inverse times the volume of G of R. And well, the determinant of L inverse is just 1 over the determinant of L. Now let E be a bounding rectangle of A, and let P delta be a partition of E into cubes R with centers XR and whose sides are all less than delta. And let P delta star be the set of all cubes in P delta that intersect A. Then the volume of G of A is less than or equal to the volume of G of all of the subrectangles that intersect A. Right? Because all cubes intersecting A, if I take their union, they completely contain A. Well then, using the result right above, I can multiply and divide by the determinant of the derivative of g at the center point. Right? So all I've done is multiply and divide by the same thing in anticipation of using this result. Now, the derivative of the determinant of the derivative of g at the center point, that's just a matrix. So I can use this result here. I'm assuming that my matrix is invertible from the change of variables hypothesis. So this fraction becomes the volume of the inverse of that matrix times g of r. And I'm left with this determinant here. Now recall that we bounded the volume of a cube deformed by a change of variables. And so let's use that result here. So the volume of g of a is less than or equal to the sum over all subrectangles that in my partition that intersect a of the determinant of the derivative of g evaluated at the center points times the maxed value over c in my subrectangle. That should be a regular r, not a real line r. Right. Now here I still have my inverse of my derivative matrix evaluated at the center point times my derivative matrix evaluated at some c, where c gives me a maximal value of this norm in the infinity norm, times the volume of E. Now remember, I assumed that G is class C1. That means that the derivative of G is continuous. Therefore, if I take the limit as the size of r goes to 0, in other words, I take the limit as delta goes to 0, then every value in my partition cube will shrink down to the center point, xr, and I'll get the identity because I have the inverse of a matrix times this in the limit. Furthermore, by Darboux's criteria for the integral, we get that the volume of g of a is less than or equal to this if I take this right-hand side, if I take the limit as delta goes to 0. So that would give me the integral over a of the absolute value of the determinant of dg. So we have this result. The volume of g of a, which is the integral over g of a of 1, is less than or equal to the integral of a times the absolute value of the determinant of my change of variables. Now, if f were not constant, then we could apply the machinery behind Lemma 2 to show that the integral of f over g of a is less than or equal to the integral over a of f composed of g times the determinant of dg. That's because when we break this down into all of our upper and lower sums, then I get a constant on each subrectangle. Now we could apply this same result to this integral and use the change of variables formula g inverse. Right, a is g inverse of g of a. So then let's use this result here, where my integrand instead of f is all of this. Well then, according to this result, that's less than or equal to g of a, f composed of g inverse. By the way, that's just f, we know that. The determinant of dg composed with g inverse times the determinant of g inverse. Now, we should recognize that from our chain rule as just the derivative of G composed of G inverse. Now, G composed of G inverse is the identity, and its derivative is the identity, and the determinant of the identity is 1. So I just get the integral over G of A of F. So this integral is greater than or equal to the integral of F over G of A, and less than or equal to the integral of F over G of A. Therefore, it holds that they must be equal, which is precisely the result of the change of variables theorem. Well, that's it for today.